Stanford University.
And this is an energy seminar, and what I'm going to tell you has nothing whatsoever to do about energy. Right? This is about how we engineer the planet. It's about the fact, an uncomfortable fact, but it is a fact, that we have the technical ability to do this with frightening level of sort of basic technical ease and frightening low cost. That doesn't mean that it works perfectly. It doesn't mean we understand the risks very well. It certainly doesn't mean that we should do it. But I think understanding that there really is a sort of level of technical reality here is important because it forces us to think about the public policy problems that this raises in a serious way. And if there's one thing I want you to take away from this, it is that we cannot afford to put our heads in the sand about the underlying reality that we can do it. And we have to engage hard with the public policy problem about how we manage this, this power. And I won't say that much about this. I'd actually decided to put more technical slides in this talk because I thought it'd be useful. I'm sort of assuming some people have had a general idea about this topic. I thought it'd be useful to give you some understanding of the technical side of it. But in questions, I'd be really happy to respond. I'm involved in, I think, all of the various international efforts that are now moving to try and understand how to regulate or control this technology. And I think that fundamentally, the hard topics here are not technical. They are all the social problems of how we manage it. But that said, let me move on and tell you a little bit about what it is. So first, what it is in the most simple sense is, if you think of the names for the ways we manage the climate problem in this scenario is we make climate forcing, emitting CO2 and other things that alter the climate, interact with the climate system in some way, and then that affects human and of course non-human too, but I'm leaving that off, welfare in some way. And we can deal with it by mitigation or by geoengineering or by adaptation in principle. And that basic fact and that schema has been known for a very long time. But that is in a sense what it is. So it's not about energy. Energy is what we do to reduce the amount of CO2 emissions. And let me let you in on a big secret. There is nothing we can do for solar geoengineering that gets us out of the long-run necessity to cut our emissions to effectively zero. It can help us manage the risk in some ways that might be quite important. It might allow us, whether we think that's a good idea or not, to delay, but it cannot get you out of the need to cut emissions because the compensation, at the very best, is fundamentally imperfect. I'm going to start with sort of the best argument for why you should be scared about this, and this is something I could say in 100 talks, but I think this cartoon absolutely nails it. And it's actually, the more you think about this cartoon, it really is clever. So as I'm going to say in the next few slides, of course, when you put carbon in the atmosphere, it stays there basically forever. I'll give you some numbers around that in a minute. And so, the search for a breakthrough technology to solve climate change continues, and we hope it's a time machine that will take us back. And always with this guy's punchlines, this guy says, the punchline's down here. This guy says, we better hurry. And the other guy says, no, that's the great thing about a time machine. So in some ways, geoengineering is a bit of a time machine, to the extent that when you put carbon in the atmosphere, it stays there forever. We traditionally think of this as a one-way valve. And when you think about the risk management problem of climate change, you think about it traditionally as a one-way valve. And this gives us some limited, imperfect ability to back up. This is not a new idea, nor is climate change. So this report got to President Johnson's desk when I was 2 years old in 1965. And it was the first report that really told you everything you needed to know to say you had a serious problem with climate change. And it's actually worth reading because it's a lot shorter than the IPCC, and it in some ways says the key things you need to know at least as well. And actually in the course of one time writing something on the history of geoengineering, I went through a bunch of these old reports, including National Academy 1977 and the MIT Man's Impact on Climate in the early 70s. And you get this fantastic sense of just how much we knew how early and how little we've done. And geoengineering was in there too. In fact, it was about the only thing they really suggested that we ought to do. I'm not claiming this is what we ought to do. This says something profound about the way people's thinking changes and the way the political framing changes. But the underlying understanding that doing something other than just cutting emissions was a possible way to help manage the risk, that understanding was in essentially all the climate assessments up until the last decade or so, where it became sort of politically, or 2 decades, where climate change became much more visible publicly and it became politically incorrect to talk about this. And then that, in turn, was broken by Paul Crutzen's article 4 years ago, or whatever it was. So a couple things about framing. we don't know exactly how much climate risk we have for a given amount of CO2 in the air, and we're not likely to know before we just find out by experiment. And that's been true for a long time, but it's a fact that people often sweep under the rug. You'll get politicians happily talking about whether the target should be 400 or 500, whatever is ppm, but of course we don't know what that target should be because we don't know the climate sensitivity. And this is some results that we published recently in PNAS that go back to an earlier paper that Granger, Morgan, and I published in the early 90s, where we interviewed a bunch of climate experts and did this stuff called sort of structured expert elicitation to get people's sense of the climate sensitivity. And I'm not going to bore you with the details except to say that it's pretty clear that most of these experts believe there's substantial probability, larger than IPCC, even though these are basically the same experts who play in IPCC, substantial probability that climate warming could be bigger than 4.5 degrees C for something equivalent to a doubling. We asked the question in a slightly more clever way this time. So it's that underlying uncertainty that makes the problem so hard. And then a second factor, which is inertia. So we have this idea, I like using the nuclear waste analogy because people think of nuclear waste as being such an awful long-lived thing. So if you compare a year from discharge from a reactor to 1,000 years out, in 1,000 years, most efficient products are gone. So you're down by about a factor of 1,000 in the radioactivity. If you think about emitting CO2 with exponential increase, which we've been doing, and then you stopped, 1,000 years out, the climate change is only down by less than a factor of 2. So in that sense, the shadow that we cast on the future with climate is actually much bigger than the one we cast with nuclear waste, which gets you thinking about how to think about the risk of nuclear waste, but that's not my topic here. And then let me also say something about inertia, because the key framing I want to get you to think about here is the combination of inertia and uncertainty is what makes the climate problem so difficult and dangerous, and also one of the reasons I think it's important to have, not to do geoengineering, but to have or understand whether or not we could have the capability to do it. So another reason there's a huge amount of inertia is, let's say we finally get serious about climate change. I mean, right now, mostly what we've done about climate change is agree to talk about it and feel good about talking about it and make commitments to things we're going to do in 40 years out after we've left office. And so we can all feel good about that and actually do nothing. And that summarizes like 80 or 90% of what's actually happened so far, although California has done better than my province has done by far. But still, that's sort of the reality. Let's say we got serious. Let's say that politicians decide to sort of turn the wheel and actually do something. Maybe we're going to put on a carbon tax with recycling or whatever it is. The purpose of that is not to punish emitters. It's to replace the high emissions infrastructure with some low emissions infrastructure. I don't really care if that's solar or wind or nuclear, whatever it is, or CCS. But this is expensive, long-lived infrastructure. And you build that infrastructure slowly. I mean, if you send a signal by putting on a carbon price, the infrastructure only begins to grow kind of linearly once you've sent that signal. But building infrastructure doesn't directly solve the problem. Building infrastructure just reduces the rate of emissions. But emissions aren't directly the problem. It's concentrations that are the problem. So you've got to integrate twice to get concentrations. And that's why there's so much inertia. From the time that you begin to send a serious signal to the time that you see real action, counting both the inertia of the economic system, all this long-lived infrastructure you've got to replace, and the inertia of the carbon cycle, from going from emissions to concentration, plus that little bit of inertia from ocean thermal inertia, you have this gigantically inertial system. So you're steering a supertanker from the time you begin to really change emissions. So that is the fundamental reason the climate problem is so hard. If you didn't have inertia, it would be rational to do what some people suggest we should do, which is wait till we know how bad the climate problem is. So if the scientists are uncertain about how bad the problem was and there's no inertia, it would be fine to say, let's just put off doing anything until we know what to do, and then we'll figure out how much we want to pay. But you can't do that given the inertia. So it's that combination that's so dangerous. And the reason geoengineering is potentially interesting, and I really mean solar geoengineering, I'll get to that in a second, is that it gives you some capacity to go backwards in time. It gives you some capacity to manage the case where you find out that the amount of CO2 you have in the air is greater than you can tolerate. Because remember, if at some point we find out that Greenland is really melting and we really shouldn't have the amount of CO2 in the air that we have, stopping emissions doesn't solve that. Stopping emissions reduces the extent to which we are adding to the risk in the future. Stopping emissions doesn't do anything about the risk we've already built up by putting CO2 into the atmosphere over centuries. So there are two completely different things that go under the name geoengineering that don't have much to do with each other. I'm only going to talk about one of them. So there's this stuff called solar radiation management. Management is not necessarily the right term. This has become the term of art. It sort of implies that you can manage maybe more than you really can. There's a bunch of ways to do this, but basically this is all reducing the net radiative forcing of climate, reducing the amount of sunlight the Earth absorbs, And all these things share the following three characteristics. They are all fast-acting, they are cheap, and they are fundamentally imperfect in ways that I think can't be fixed. And then there are a bunch of ways you could remove CO2 from the air. And full disclosure, I run a startup company that works on that one. And these things all more or less share the same properties. They may have a lot of local risks, like my machine might kill babies or who knows what. But they have a global benefit, so local risk, global benefit, just like lots of other low-carbon technologies. And they're all relatively expensive because you actually got to deal with all the CO2. And they all are effective in the sense they really would get the CO2 out of the air. So these things look much more like conventional mitigation than this. Indeed, they're really almost completely like conventional mitigation, except they allow you to go backwards in principle. And I'm going to leave them off the table because I think the governance challenges are much smaller, although I think they're very important, and that's why I work on one. I'm going to skip this and say so let's just jump into how well it works. One's natural assumption might be, first of all, if you warm up the world with CO2 and then you cool it down by turning down the sun, there's no question you can get the planetary temperature back to where it was when you started. Two curves have to cross. But you don't get the climate back to where it was because climate is much more than just the global average surface temperature. And you might expect that the climate compensation would be really bad. You might expect that you would have it be, for example, the pole to equator gradient would really look different, or the seasonal cycle would really look different. And in fact, who knows what reality is like, but in the climate models, essentially all the climate models we've looked at, the compensation is remarkably good. So I'm going to show you some slides from Ken Caldera's work that gives you a sense of how good that compensation can be. And it's pretty good in precipitation too. I'll give you a sense of that in a second. In models, maybe not in reality. There's lots of things that the models leave out, so it may not work as well in reality as it appears to work in models. I worked with some students, both a climate scientist and economic student, really trying to look in detail at how imperfect it is at a region-by-region basis. And so this gives you a sense of what temperature and precip look like in all these different regions. And the blue is the 2 times CO2 world. It's not actually quite 2 times CO2. This is a linear wrap in the Hadley climateprediction.net model. And the red is in a geoengineered world. And the units here I have to explain. The units are not physical units. The units are the change in temperature divided by the interannual variability in that place. So it's a kind of a normalized variance from the mean. So if this says here, this says that it's warmed by twice the typical deviation, and same for precip. And what you find is it's imperfect. There are some places that do worse off, so that you can find places there where as you turn up the amount of geoengineering, you really are getting worse. But most places do pretty well, and in crude terms, we can actually calculate in multidimensional space the angle between these two things and sort of figure out how good the compensation is. And the compensation, at least in these models, and people are just beginning to use crop models in a serious way, and we didn't do that, seems to be, at first order, amazingly good. So, the Pareto optimal solution, that is a solution where you go as far as you can towards optimality but nobody loses, is like 85% as good as the optimal solution, which for economists in the room hopefully gets you a sense that inequality is less important than a lot of people assume here. In this model, without a real crop model that nobody's run yet. So this is all early stuff, and we could be completely wrong. The bottom line, and I'll come back to why this is true, is there has been essentially no organized research on this topic. There hasn't been a US federal program. There still isn't one. I'm on a committee that's helping to shape what one might look like. There are now formal programs in the UK and in Europe and separately in Germany, but there are no formal organized research programs in the US. There are individual researchers. So we've got funded through NSF grants over now a decade and a half at Carnegie Mellon to think about this, but in a small way where that wasn't the headline of the research grant. So, professors tend to follow the money, so if there's no research grants, people don't work on topics a lot. Let me give you a sense of some of the underlying engineering. As I said, engineering is not the dominant problem. See, the dominant problems are all social. They're the problems of how you control something where an individual country can have tremendous leverage over the whole planet's climate, and where there are winners and losers in ways that really could be unpredictable. And not to frighten you, but I think you can imagine scenarios that lead to war. And that's why we're engaging a bunch of the national security community that are in serious ways. But let me give you a sense of some of the engineering, just because a lot's happened. So maybe I'll skip over this. There's all sorts of ways you could do this, but the standard idea has always been, and really all the papers, essentially, aside from a couple that I've written and maybe one or two others, have looked at assuming that we copy volcanoes. that we put SO2 in the stratosphere just like volcanoes do. And we know that after, say, Pinatubo, the Earth got colder by about ½ degree C. And there's some thermal inertia, so actually the effect would have been bigger if you just kept the same forcing for a long time. And that also gives you some kind of existence proof that we did that and things didn't go totally haywire. There was some ozone loss, precipitation went down just like you expect, crop productivity went up actually on a global average basis because of the direct diffuse radiation. So it tells you something. It doesn't necessarily tell you that much. So the obvious answer everybody's assumed is to keep putting SO2 in the air like Pinatubo did. It's not clear that that will even work. So there are a couple papers here that I and then this group at ETH and Deborah Weisenstein are the core of. And I won't sort of deal with in this talk about whose paper's who. I've got a list at the end. But if you want to make a scattering particle in the stratosphere, there's an optimal size. This shows you the scattering efficiency of this particle. That is just basically how much light it scatters per unit mass of the particle. And particles that are very small and very big are very useless. And it's not hard. I mean, this is really basic physics, easy to get. It's also true that particles, as they get bigger, fall out a lot faster. So that's an even bigger effect. These heavy particles fall out of the stratosphere quickly. So the problem is the following. If you add SO2 to the stratosphere, SO2 doesn't condense. It's a gas. SO2 doesn't make particles. SO2 has to oxidize to H2SO4, and that takes about a month. And only then does the H2SO4 make particles. But then it's essentially, from a chemist's point of view, sort of appearing all over the stratosphere when that reaction happens. And where does it go? It all goes to the existing particles. And so the existing particles grow, and the big ones grow preferentially, and you get a particle size distribution that's all skewed to very big particles. So if you just keep putting SO2 in the stratosphere, you end up driving it all to a big particle size mode, which is both very inefficient and it falls out quickly. And it turns out that you may not even be able to get, and I'll show you this in the last slide, this was the first paper, you may not even be able to get 4 watts per square meter with any amount of SO2 in the stratosphere, at least with simple schemes, if you just inject it. So I'll just focus on this one. This is global average forcing in watts per square meter, so 2 times CO2 is around here. And this is the millions of tons of sulfur you're putting in the stratosphere. And most models have assumed a linear line because they didn't do any physics of these small particles. And so they sort of assume that, oh, you put 4 or 6 million tons a year and you get 2 times CO2. Nah, the real world looks more like this. It asymptotes because you're making all these big particles and they're falling out faster. So we sort of step back and think, okay, well, how would you actually make particles in the stratosphere? This is really engineering now. Well, so in principle, you could put some high vapor pressure gas in, some gas that doesn't condense, and let it react to condense. That's what SO2 does. That's the standard idea. You can also release some gas that wants to condense very quickly in the trail of an aircraft. And then it turns out you can control the particle size distribution really well. It's easy to do. In principle, you can make liquid droplets. In engineering terms, this is really a pain, but in principle, you could do it. And in principle, you could do solid particles. I'll get to that in a second. So I focused on this one. And the basic idea is that if you let a plume off in an aircraft by just changing some little details about the way the turbulence works that are easy to adjust in engineering terms, you can make a particle size distribution more or less how you want it. And so I got a guy who had air pollution code that was good at doing this, and we couple it up to all these people who do these global sulfur models that have been doing it for Pinatubo for years and for ozone chemistry. And the bottom line, I'm going to sort of skip through, actually I'll skip through some of this, is that at least in the first paper that may be nonsense and totally wrong, we totally solved the problem. So this is what it looked like with the old case, and this is what it looks like where we control the particle size better. And it might be wrong, who knows, but part of what this tells you is that you need to do a little engineering to understand what's going on here. And that if you don't have any research program, nobody gets funded to do the work, so nobody knows. So this does appear that you can actually get much smaller particle size distributions by doing this kind of spraying, and it does appear that that would be, allow you to get 4 watts per square meter. Should you want to do that? In fact, it's extremely unlikely you want to do that. If it ever makes sense to do this, it probably makes sense to do it just a little bit and work your way up, because the benefits, well, we'll get to that. That gives you a sense of what happens. Minor fact, smaller size means more surface area, but more surface area means less ozone. So just to give you a sense of some of the trade-offs here, the ozone loss using the ETH ozone model, actually our method makes things look a little worse because smaller particles have bigger surface area to volume. In principle, there are ways around that. So you might want to put alumina in. Alumina has a very high initial refraction. It's very small. It doesn't coagulate. You could go down this engineering trail a long way. My biggest summary thought, which really is the one that matters to everybody who just doesn't like doing engineering and wants to think about public policy, is the big lesson number one. It is much easier to think of new ideas like this than it is to untangle the extent to which they would work in the real world or what the risks might be. So here, just a few of us thought up this new idea, and we got a nice paper, and it might actually be really useful in managing the world's climate. But to actually really untangle the extent to which this would work or not in the real world, what the risks and side effects and gotchas might be, is far harder than is to think of the original idea. And there are going to be more and more and more of these ideas coming at you. And so one thing we want to think about when we think about how to manage this problem is to build the capacity to really think through some of these trade-offs. There's a huge scope for new methods. After this, I'll show you very quickly this one little nanoparticle method that I've thought of, but it is even more crazy. The environmental hazards cannot be assessed without knowing which techniques might be used. So why am I wasting my time doing this geoengineering? Because if we just look at the environmental risks of geoengineering, and to be clear, if I was in charge of designing a research program, I would put most of the effort of the research program looking at the environmental risks and side effects. But if we just do that and don't do any engineering, then we'll only look at SO2 forever, because we'll assume that's the answer, because that's what the early paper said. And so the point is you have to couple them. You have to actually have some people who are thinking about how you'd actually do the engineering and try and minimize the risks, and then a larger group of people trying to think about how it wouldn't work and what the side effects are. That's, to me, sort of essential for having a serious program here. But otherwise, you have this sort of looking under the lamppost problem, which I think is where things have gone so far. So I regard the stuff that I've done on looking at new methods more as sort of illustrating just how big the scope for new methods is. I'm not arguing any of these methods is necessarily better. We don't know, we haven't done remotely the kind of work it would do to really understand the trade-offs here. I should say we funded a company called Aurora, which does high-altitude aircraft, and we've looked a little bit at the costs of doing this. Because some people, not because I think we should do this tomorrow, I don't, absolutely not, but because some people argue that this is actually expensive, and I think it's important to know some facts, and the facts are it's frighteningly cheap. That's not a reason to do it, it's just a fact about the engineering world. So the cost of delivering material into the mid-stratosphere by several different ways, hybrid airships or conventional aircraft or some of these other things, the costs are sort of bucket kilogram. That's a bucket kilogram cost because it's 1 billion tons a year, or 2 bucket kilogram costs, which means the total cost to do this are sort of $1 billion a year kind of annualized costs, which remember in a now close to $60 trillion global economy is basically zero. It means that even the smallest states in the world, or among the smallest states in the world, can in principle leverage the whole world's climate. A very frightening thought, but it's important to know where we are, and that's where we are. I'll skip through this pretty quickly just to say, this is now published in a paper in PNAS earlier this year, but I gave you a sense of just the most obvious thing, just making particles, but you could actually engineer particles that have more fancy properties that could get around, in principle, some of the downside problems in the stratosphere. So if you have I'll tell you the simple version, and then I'll kind of skip to the endpoint. Imagine you have a particle where the air is very thin. So this is my particle, and the air is so thin that the average distance an air molecule goes before it hits another air molecule is bigger than the size of the particle, which is true in the stratosphere pretty easily. And if one side of the particle was warmer than the other, then the particles would sort of bounce off faster on that side, and the thing would feel a force this way. This is very important in interstellar disks. This is actually not the way it works in the atmosphere. The way it works in the atmosphere is a little more complicated, and I'm going to skip over that. And I'm going to skip over this. And in fact, I'll skip over the whole thing and just say, you could make particles that levitate in the atmosphere. And indeed, there's some evidence that particles already do levitate at the top of the mesosphere naturally. And this is really basic physics that nobody disputes. You can make self-levitating particles that stay where you want them to be. There's really two stable points, the upper stratosphere or the upper mesosphere. And you can engineer particles that have particular properties. And you can engineer some properties that I mean, there are two reasons that this might be good. One is that it gets them out of the stratosphere, where you then don't catalyze the chlorine nitrate to active chlorine, which causes ozone loss reaction. And it also you could make particles that were little plates, and little plates don't scatter radiation, and so you could have a kind of cleaner alteration of the global sunlight flux. You could also trap them near the poles, perhaps. So the reasons that this might be interesting are longer lifetimes, except this is where you start to think about the social science. Are longer lifetimes good? How long a lifetime do you want? It's not clear. And so I think I've been thinking a lot about reversing this and saying, if I'm cognizant of the real ways in which human societies make mistakes with technology, what is the kind of geoengineering technology I'd like to have that makes it least likely it'll be abused? You can get them above the stratosphere. You can concentrate particles near the poles, which is where there's the polar amplification of global warming, and so it might be just what you want to do if you want to maximize the effect of reducing Arctic warming while minimizing the side effects in the rest of the world, and the last one as well. And it's not crazy. Some people said, oh, you couldn't possibly do this at a reasonable cost because nanoparticles are too cheap, but this is a little scaling calculation that suggests that that's maybe not true. You can actually buy now, I knew it was cheap when I found that they were quoting me in tons. You can buy little round spheres that are about a micron size and have wall thicknesses that are a small fraction of their radii. You can buy those things at where they're priced in tons nowadays. So let me say about detection and attribution. And this matters because the question is, how would you test any of this? How would you know anything about what happened? Both how would you test it, but also if one country did it and another country argued that it was affecting it somehow, how would you detect? So let me actually put a scenario, give an example of a scenario. So let's say that India became concerned that the heat stress on crops could really reduce total crop productivity in a way that could really impact their ability to feed their population. And that they did a bunch of early studies that indicated that putting a half a watt per square meter of global sulfate aerosol forcing or some other aerosol forcing would reduce the peak temperatures. And this wouldn't bring you back to pre-industrial or anything crazy like that, but it would reduce peak temperatures enough to really have a benefit. And there's some, the early evidence is that what I said is in fact true. And let's say they go ahead and want to do that. And let's say the Chinese thinks it makes their monsoon worse. Whether or not that's true really doesn't matter. So these are two nuclear-armed states. We don't have any clear mechanism of how to settle this dispute about how to set the thermostat, and a thermostat that isn't the same in all places. So I'll just say a little bit about detection and attribution. There's some strong statements out there, like this one, that basically says you can't do anything except at full scale. And that obviously isn't really true. This is a signal-to-noise problem. In fact, even if you do it at full scale, you don't know what the effects are. Of course, we're doing the CO2 experiment right now. We've got 390 ppm CO2, and so that's the scale we're at. Do we know exactly what the climate effect of that is? No. We know the signal, but we've got a lot of noise in the system, so we can't untangle exactly what the response is. And the same would be true of geoengineering. So let's say we go up to 500 ppm or something like that, and we geoengineer. You could geoengineer, and you still wouldn't know exactly what the effect of geoengineering was because you've got a noisy system. And there's nothing magic about full scale. Clearly, it's a signal noise problem. As you do it with a bigger forcing, you learn more about it. But there's no black and white where you suddenly learn and otherwise didn't know. That's just a fact everybody should know, but in the policy disputes about that, that fact gets lost. This gives you, so first statement. This is we've done fun climate model experiments where we actually run them with little perturbations, and the perturbations go from 2 years out to 64 years, and we run big ensembles and basically look at how climate models respond to little periodic perturbations at different timescales. And the bottom line here is that this tells you how long you have to wait in years to measure accurately the response in a grid box. And the answer is a really long time, longer than is relevant for policy. Therefore, estimating regional responses is hard, or I could pretty much have written impossible in practical terms. So you're not going to know by measurement exactly what the response is in your part of the world. Of course, the same thing is true for CO2, exactly. And of course, it's not clearly a bad thing that's true for CO2. People argue about the kind of Rawlsian veil of ignorance being a good thing. So right now, we don't know exactly who the winners and losers are under increased CO2. And a lot of climate scientists naturally think, oh, it'd be good if we had more information and knew. Not clear. It might actually be harder to negotiate a deal about climate if everybody knew exactly who the winners and losers were. Same might be true here. So this is where the social sciences and the hard science interact in some interesting ways. This gives you a look at the frequency response. This is periods. This is short period forcing to long period forcing. And first, just look at the frequency response of precip here, which is flat, and temperature here, which rises. So basically, if you perturb the climate in some way, if you perturb it on a slower and slower period, the temperature response just keeps getting bigger. That's basically because of just the thermal inertia of the ocean. Was the precip response stays about where it is. That tells you something important. People who say they can judge the effect of geoengineering from these short perturbations like the volcanic perturbations at Pinatubo are misjudging it, because we know those perturbations that if you look at the ratio of the precip response to the temperature response, that ratio, the precip response looks much bigger compared to the temperature response for short period than for long period. And so looking at, say, the effect of Pinatubo and thinking that that's the right measure of the long-term precip response is certainly wrong. That's not saying that we know exactly what the precip response is, but kind of naive statements like that are not credible. We've looked a little bit at this sort of signal detection attribution problem. I think the bottom line is the following. Whether one could imagine doing this in the real planet, I can't say. But if you did a perturbation of, say, a half or a third of a watt per square meter, so something big enough that nobody could call this a small experiment. At this point, you are altering the world, but still much smaller than the total effect of CO2. And you did that perturbation in a periodic way for 2 decades. You could measure the response in some really useful ways. As a side product, you could say something useful about the overall climate sensitivity to CO2, which would help you understand the climate risk. So now I want to try and wrap up and say some more general things about this problem. So I want to argue that the 3 important characteristics, as I said in that earlier slide, are this cheap, fast, and imperfect. And I want to say something about what the policy implications are of each of those 3 things. So first of all, and I want to, for each of the cheap, fast, and imperfect, make it clear that this isn't just because some study said so. These are for deep underlying things that I think will be robust to new ideas and new studies. So the reason that it's cheap is basically that so little mass is involved. You can alter the whole global climate roughly as much as 2 times CO2 by moving twice my mass to the stratosphere every second. It's just not very much mass. And that's the underlying reason why it's cheap to alter the system that way. This gives you this fantastic leverage over the climate for better or for worse. Frightening leverage. And I think that's a robust fact that we just have to live with. It's imperfect. I showed you this slide before, but that imperfection is fundamental. So for reasons that we understand really quite well on theoretical grounds, you cannot compensate, for example, both precipitation and temperature. So if you warm the world up by adding CO2, then turn down the sun enough to bring back the global surface temperature to what it was before, it is for sure true that global average precip is smaller. The hydrological cycle is slower. And we understand why that's true. In simple terms, it doesn't take a climate model, it takes a pencil and paper. So I think that's a stable, robust result that will always be true. So you cannot perfectly compensate away the effects of CO2. Another way to say that is if you said to yourself, oh, this is so cheap, it's a great solution, let's just do this and forget about cutting emissions. That would, in the short term, reduce the impacts for sure, but in the long run, the impacts still grow to infinity. That is, if you just say I'm going to hold a global temperature constant and increase CO2 to infinity, the impacts grow to infinity. I mean, obviously, some impacts like the direct impact of CO2 on ocean geochemistry are unaffected by this. And other impacts still grow no matter what. So let me tell you a little bit about the policy implications. So the fact that it's cheap means that the fundamental policy challenge here is control in a way that's very different from the problem we have for emissions mitigation. For emissions mitigation, we need most countries in the world to be willing to spend substantial 1% class GDP to reduce emissions. And we have this coordination problem, very hard, public goods problem of coordination to get the world to play ball and cut emissions. The problem for geoengineering is different. We have really a problem of control. For almost any country except the very smallest, the actual costs of doing this are very small. The issue is about coordination and control of an activity that essentially any country can do unilaterally. Very, very different public policy problem. We need different ways to handle that problem, fundamentally different. The fact that it's fast is one of the fundamental reasons to take it seriously. So I started my lecture by saying that one of the underlying reasons to worry about climate change is this combination of uncertainty and inertia. So we are aiming for the sort of likely spot. So, well, right now we're mostly just talking, doing nothing. But if we had sensible climate policy that cut emissions in a kind of, we all will have different views, but in some relatively sensible way, so we're heading towards zero emissions, in 2050 or something like that, we would reduce the probability of really terrible climate outcomes a lot, but not eliminate it. Even if we do that, there's still a probability that we roll the dice and we find that climate sensitivity is 6 degrees C and Greenland's really melting. And this gives you a way to manage that risk, not eliminate it, but manage that risk in a way that is clearly important. I think you're just, in my opinion, it's not credible to say that's not a potentially useful and important thing. And the fact that it's fast is important because you can make the decision after you find out what the climate sensitivity is, right? The whole point about emissions mitigation is we're making most of the emissions mitigation decision before we find out what the climate sensitivity is. This decision you get to make after, that you can do because it's fast, and that's sort of a fundamentally important way this is different in the way climate policy plays out. And finally, the fact that it's imperfect means that it can't be a perfect substitute. And it means there are going to be winners and losers, just like there are winners and losers for CO2, but they're different winners and losers. So this makes the problem, if anything, harder to solve. You've introduced another dimension of complexity into the managing the planet's climate problem. Well, if we were going to do research, what would it be like? So I think there are really three categories of things. The first category of things is basically all lab stuff. You could do climate modeling. You could do engineering studies of very small deployment systems. You could do lab measurements of relevant quantities. So for example, some colleagues of mine, actually Jim Anderson and co at Harvard, are going to do this. They're going to look at how some particular particles might or might not be active in the stratosphere in terms of the catalytic chlorine destruction cycle. So you could start actually looking at that. That's a laboratory study. You could look at ways to actually, as I said, to build the hardware. So Armin Neukermann's here, wherever he is working on clever ways to make sea salt aerosols. One of the technologies I didn't mention to you is that you could spray sea salt aerosols in boundary layer clouds and make them a little whiter, for example. So you can study how to make those aerosols without altering the climate. You can do process experiments. These are experiments that try and understand the processes that would be necessary to understand in order to say something about how this would work at scale, but they don't tell you the large-scale atmospheric response. That's the key distinction. These experiments can be done without any large-scale atmospheric impact, for sure, but they have important political impacts that matter, and so we need to think hard about how we manage these experiments. But to give you a sense, so picking up on the one I mentioned about sea salt aerosols, we still know very, very poorly how much clouds get whiter for every unit of these fine aerosols you put in the boundary layer. So you could imagine simple experiments at quite small scales that would have no large-scale environmental impact for sure that would tell you that. But the fact that they would have no large-scale environmental impact doesn't mean that they shouldn't get some scrutiny. And they should get scrutiny because they're leading us down a direction of giving us this sort of greater level of leverage or control over the planet's climate. And understanding how we start down that road in terms of transparency, who makes the decisions, control, openness, blah, blah, blah. Those things are crucial in setting up some kind of stable regime that's able to make the more serious decisions about subscale deployment. And that's my last category. I think beyond process experiments, you're basically talking not about experiments, but about deployment, but deployment at some small scale. So should we have a research program at all? There are some people who argue that we should not actually very many anymore. There's a lot of view that some people are arguing that, but it's hard to actually find any. In fact, the big environmental groups in the US, Environmental Defense and NRDC, for example, seem comfortable with some level of research. People have different comfort levels, but there's very few groups or people now who say there should be no research, but maybe there will be some in this audience. But if you think about it, it's not a dichotomy. Geoengineering won't either work or not work, but I think it's useful to think through this, and that's certainly what's been behind my view that in this case, ignorance is dangerous, and it makes sense for us to know a little bit more, and therefore to have some sort of research program. And it makes sense to have the government control that research program because this needs to be done in the public interest with public oversight. So let's say we expect that geoengineering either works or doesn't work. Of course, it's not going to be black or white, and let's say we find that either works or doesn't work. What I think all of us are concerned about, this thing that's come to be called the moral hazard, if that's the wrong word for it, is this box, the dangerous overconfidence box, that we're going to really be sure it works and it won't work. And that we, therefore, that certainty that it works will make us spend less effort cutting emissions, and then we'll find that we roll the climate dice in an unlucky way, and we have to do it, and it doesn't work. That's a very real worry, a worry I share a lot. But it's not the only quadrant in that box. And you've got to think about the other ones. Let's say we find that it works relatively well, not perfectly, but it works relatively well to limit damages in, say, the high Arctic, place I spent a fair amount of time and really love. I think we'll feel foolish if through political correctness we don't think about it for 50 years, let the high Arctic warm up, and then realize, oh, we could have actually done something that would have reduced that a little bit. So I think you really have to think through all sides of the box and begin to think through how to manage a research program that tries to reduce some of the what's become to be called the moral hazard effect, although I think that's the wrong wording. But just to be clear, and that's really what was captured by that cartoon at the beginning that said it really better than my academic slide. The key worry here is the following. I spent most of my career working on climate change, not working on geoengineering. I spent it working on the regular climate problem. And when I go into politicians' offices to argue why we should do something about climate, one of the things I routinely say is I say, this is an insurance, a risk game. It's not just about the meeting expectations. We have to worry about these very bad climate outcomes, and that's why we want to hedge our bets and really cut emissions. That's an argument that I think many people in this room have made in various circumstances too, and it's a good argument. But to the extent that we have something that helps you manage that worst case, then it's hard to make the argument. And that arguably means a weaker commitment to cutting emissions now. And that's the underlying fear that many of us have, that I think has been the fear that was behind the taboo that said that we really weren't going to talk about this in public and not research it. Of course, that's not the only reaction that's possible. This is an empirical statement. There are various different reactions, both in terms of the regular public and politicians. So the opposite reaction is that the public will say, well, if pointy heads think we need to shoot nanodust in the stratosphere, basically if people are so concerned that they think we might want to do this, then the climate problem really must be serious and we should get going. Now, there are a lot of variants of this. I have an econ student who's actually looked at this in a two-player game model. A standard model has been used to think about the public action problem for climate change. And he shows that depending on the settings of the model, geoengineering can actually produce more climate action. That's when one party seeks to essentially preempt the other party's geoengineering by doing more emissions mitigation than it otherwise would have. So it's subtle. It's not obvious the way this changes the climate policy game. And I think the biggest lesson that I hope biggest thing I hope people will take away is don't be so sure what the answer is. This needs a lot of careful thought. And this will alter the way the climate game looks in a variety of ways, some of which could be hideous, but some of which also could be positive, both by actually reducing the risk and by changing the winners and losers and changing the structure of how we think about the climate problem in ways that might get us unstuck, because we're clearly so stuck right now that we're not doing much of anything. Thank you very much.
Well, I'll be surprised if there aren't questions, but so we're here.
Speaking as an engineer and statistician,
Yep.
I applaud your approach and the suspicious geoengineering because it's much like a carnival.
Find all my people
Expects right now.
Yep.
But I'm wondering why, I have two parts of the question. Why have you stopped at 1970 for reports about warning of climate change when you know that for 100 years before now or more, folks were warning us, such as in 1896, Svante Arrhenius, the Nobel chemist, warned about the effects of acidification of the atmosphere with carbon dioxide. But why not actually start there to indicate how far behind we really are?
That's great.
The other side of the question is, CO2 doesn't just affect climate.
Of course.
In fact, we very well may experience far more serious problems than climate very soon, because already off the Nordic Peninsula, you have acidification in the atmosphere, in the ocean, that is preventing plankton from forming correctly, and 70% of all the protein in the world that's used by humans in the sea, 100% of all the fish depend upon plankton.
Yep.
So I think that a little broader perspective might be good in terms of both going back in time and actually covering the effects that we are likely to see in our lifetimes, not in 2050, but in our lifetimes.
Sure. So, I mean, I did say, I think pretty clearly this talk, that this doesn't do anything about CO2, which acidifies the oceans. The question, yeah, agreed completely. We say it all the time, yes. But that's not in itself a reason not to think about managing some of the other impacts of climate, which are pretty powerful. And indeed, it's not even completely obvious that this doesn't do something useful about ocean impacts. And there's a bunch of studies we can go back and forth about this, but clearly it doesn't deal with the primary impact, which is CO2. as to why I couldn't go back to Arrhenius, you can go either way. But I think actually, in terms of intellectual history, Arrhenius got an amazing amount right. It's stunning if you go back to that paper and look at how he actually calculated this latitude band by latitude band calculation. I guess he was getting divorced at the time. Apparently this is true. And he may have, I mean, if you've ever gone back and read the paper, it's really extraordinary that he did all these calculations. But I do think it's really the early 50s, mid-50s to late 60s that we really got a handle on it, because that's when we had Gilbert Plass's high-quality radiative transfer model. So we had the first GCMs, and we're really able to put this together in a pretty coherent picture. And the point is there was an intellectual gap between Arrhenius and the post-war period, where there was calendar but not much else. And I think if you want to say when was the coherent understanding of climate that's sort of continuous with today's understanding, I think it really starts in the mid-50s.
Have any of the models taken a look into the coupling between the carbon cycle and what you're doing with what this could be doing with the solar influx? Because I know that the global temperature can affect, I mean, obviously the rains, and that can affect some of the intake of carbon into.
The short answer is yes, but again, there's been so few studies. So oh, sorry. So the question was, what about the coupling between this and the global carbon cycle? So for example, you want to shield out some sunlight. Maybe that means plants grow on sunlight. Maybe that means you slow down global primary productivity. You're going to change precipitation. Maybe that means you slow down primary productivity or change it. I know of only 1 or 2 studies that have done this in a coherent way. Both of them show higher productivity, as does actually the observations for Pinatubo, for reasons we understand, but may not tell us that much about what would happen on the full scale. But one of them is the directed diffuse issue, that if you make more diffuse radiation, in general, ecosystem productivity goes up for reasons that are obvious. I mean, basically, plants aren't shaded so much. Everybody tends to think that more productivity is good, but I'm a classic environmentalist, and that's going to change the winners and losers in different ecosystems in ways that I mean, if you believe that kind of the way nature was good, I'm not going to call that necessarily good. It's a fact. There are just the beginnings of some crop studies. In fact, I just saw some results this morning, but I can't quote other people's results. But the bottom line is that people are, the bottom line is we don't know. But at least to first order, it appears that it would bring productivity closer to pre-industrial than it would be under 2 times CO2.
Over here.
You stated very clearly in your talk that this is not something we're ready to do tomorrow. But with further research investment, the idea would be that we would at least get to a point where we could say, yes, this is a good thing, or no, right? We would have some level of knowledge for that. And I'm wondering if you could paint a picture of what types of things we would need to know to help in the research, yes or no.
Well, first of all, I think it's beyond the capacity of science to say it's something that's a good thing or not.
Certainly,
I think it's not a trivial point. It's really important. Part of the reason we got lost in the climate debate is sort of clarity about separating fact from values. The unwillingness of the scientific community to say, this is what we know, this is what our values are, and this is what we think should happen. But other people might have different values. And that actually really is important in getting to a middle ground in the climate debate that we've lost in the kind of right-left war here. So really I want to push back strongly and say, climate science cannot say what is good and bad. Could we learn a lot about the risks and who the winners and losers might be and how it might play out? Yes, I think in a sort of 20 or 30-year research program, we could know a lot about that. Would we know everything? Of course not. Would there be the potential for unknown unknowns to get us? Of course there would be. There are some ways to manage that because, again, this isn't like you sit there and decide you do nothing or flick the switch with full 2 times CO2 geoengineering. There's a lot of middle grounds. And actually, let me say perhaps the most important one that gets you, it's a bit of a slippery slope, but it gets you thinking about the fact that we're sort of doing this today. So right now, we have a huge amount of sulfur in marine shipping. Very interesting story there about the way industry moves around regulation. So you tell industry, refineries like to conserve mass. You tell the refineries you can't put that sulfur in gasoline, they're going to put it in residual fuel, and that goes to ships. So some of the ship residual fuel could be 2 or 3% sulfur. So huge amount of sulfur in that. One of the larger and big health effects, estimates of tens of thousands of people killed by air pollution from that shipping sulfur. We're just about to regulate. The International Maritime Agency is actually pretty close to pulling the trigger on some regulations that would really push down the sulfur allowable in marine shipping. That may be the single committee decision that warms the world up more than any other this decade. because by cleaning up the sulfur, which I certainly think we should do because it kills a lot of people from particulate air pollution, we'll remove a pretty significant cooling, climate forcing, and one that is actually distributed evenly just where you might want it to be, more than power plants are, and so it has a pretty large radiative forcing for pretty relatively low environmental impacts. And there are already people starting to scratch their heads about whether we should think about both sides of that. So in pure pitch mode, if I was trying to sell taking geoengineering seriously, what I would say is, let's cut the sulfur out of marine shipping because it's killing people near the coast, and let's put about it, we can do the calculation, between 1/10 and 100th this much sulfur in the stratosphere to get the same radiative forcing. It's a tiny amount of radiative forcing. It just leaves us where we are now. So it's pretty hard to argue that doesn't make the world better, because it takes the sulfur out of the stratosphere where it's making people sick. It puts it in the it's reversible. Like if you see problems in the stratosphere, you can stop. This doesn't get you outside natural variability in the stratosphere at all. It's a small number. And it puts on just enough cooling to compensate for the cooling the ships had. These conversations are getting real pretty fast. The people in China thinking about this and others. And I think that's where it gets to be a harder decision. When you think about it as a flick the switch, I'm going to do 4 watts per square meter, nobody wants to flick that switch. It's crazy. But when you think the fact that you can work your way into it, 1/10 of a watt per square meter here and there, when you think about the fact that we need to begin to think about radiative forcing, not just basically about shortwave forcing, not just about longwave forcing in managing climate, then it gets much harder. And I think that that's just the truth. It is that hard. Bert?
We techies tend to love cute technology things, and that is certainly one of the things about trying to compensate for global warming this way. But I would observe that there's been 30 years of very hard work on climate modeling. We've ended up with 23 different models at my last count, all tuned to agree with the past, and all giving different results for the future. I haven't seen enough work and enough diverse work to believe that the people who are talking about geoengineering really have the full view of what might or might not happen. The amount of geoengineering work in modeling and in developing the science is relatively small. And I would certainly support increasing that, but I'm very nervous about starting your experiments because I don't think you really understand yet what's going to happen. And I would observe, if you run down the solar flux in and leave the CO2 up, the ocean's going to continue to get more acid.
Yeah,
and so I don't know whether this thing is net good or net bad, and I'd sure like to see a lot more work before you went off to do your experiment.
So I think the answer to that is yes. So I personally don't have any experiments. I have advocated strongly that there shouldn't be any experiments in the near future. I basically think everything that you just said. So, and actually most of the other people thinking on this do too. I think it would be reckless. I mean, I would do everything I could to oppose early implementation. I think that we clearly don't know enough to do this. What I have come to believe, and I guess I've been one of the people who's helped to break the taboo and push out, is that just pretending this is impossible is not a healthy course of action on many dimensions, political, environmental, and others, that we really would be better to know more, for better, for worse. I would guess that if we have a real research program with proper public input and so on, it may help to calm this down in interesting ways. One thing it will do is it will show that it doesn't work as well as people think. So right now, it's possible for advocates to go and say, this works perfectly. Look at these early model results. And my guess is the more we look, we'll find more complexity. We'll find different ways it doesn't work as well as we thought. And that's a good thing, because it'll show people a little more of the real world. Not that you ever know the real world until you really get there. And I think that also we can use the experience of trying to govern the research program and govern it in an international way as a training ground for humanity learning something about how to govern the actual technology itself, which is there whether we like it or not. It will be there, and it's easy for us to academically sit around and say, this all seems ugly, we'd rather just cut emissions. But if it's 2050, even if we've cut emissions, and some countries are really suffering significant crop losses, they're going to think hard about this, whatever we at Stanford say today. And I think we'd be better off knowing more about it, the risks and benefits, and having the experience of the international community beginning to think about how to manage and regulate this beforehand than making decisions in a crisis. And so to me, the underlying reason to get going now is to avoid making decisions in a crisis sometime further out. But basically, I agree with everything you said. Yeah.
So we'll go over here, and then that will finish us for today.
Could you comment briefly on the pros and cons of other SRM techniques like space structures and mirrors? And speaking of space, why the picture of Europa?
I just like it as a screensaver. Good for you to recognize it. It's a good screensaver because it's sort of even-hued and stuff. And also, I personally skied across the sea ice in the high Arctic a lot, and I like thinking that that might be sea ice. I don't just say that. It makes me think maybe differently than some other people do about what the impacts in the Arctic might mean, because it means something to me personally. And the fact is, any amount of emissions cutting that we do now is not going to manage the very rapid climate change. I skied for 3 weeks on North Baffin Island this spring, and we could look at where the glaciers were now and where the glaciers were on our topo maps, which had 1950 or 1960 air photo data, and they are in very different places, every single one. You ski a week by these glacier mouths, and they're all way back. And you really can get a sense of that. It's not science, but it's real. Sorry, I'm so tired of forgetting your question. I was on a total tangent.
Briefly, pros and cons
of different methods, yeah. I think the space-based methods are probably in the end offer pretty small benefits compared to advanced engineered aerosols. And right now, we really don't know how to get space access at a reasonable price, so I just don't think about it much. I think I'll tell you some more interesting ones. I think for straight aerosol forcing, if you want to make shortwave cooling, you want to reflect more sunlight, and you want to do it in some kind of globally even way, I think it's pretty clear you want to do some stratospheric aerosol of some kind, and you want to think about ozone loss, and that's basically it. If you want to be more local, there are benefits to this sea salt aerosol technique. It's right now much more uncertain in the sense that it's really not so clear how much it works. It really may not work very well. We just don't know until we go out and try a little bit. And by the way, trying that will tell us a lot about marine clouds in ways that will help us model them anyway. There are some ideas that are literally the level of like somebody said an idea, hardly even one paper published, about how you might manipulate upper tropical tropospheric ice clouds in a way to reduce them, to make them precipitate faster. And that actually reduces the long wave forcing. And that would be much better, because if you could really reduce the long wave forcing, you really do get pretty good compensation for CO2. You still don't deal with the ocean problem. But that's at the level of one vague idea. It probably doesn't really work anywhere but some bits of the tropics, but it gives you a sense of the new ideas that will come out here. But again, the point is there hasn't been a research program, so this has been a very limited pool of people who've really thought about this at all. Okay. So I'd say it's much too early to say which one of these is better or worse. I mean, and unfortunately, this field is now filled with a bunch on the internet, especially of sort of true believers who say very confidently, this is the answer or that's the answer, and nobody has any idea it's the truth.
Okay. The one last question here.
Well, if there were a finite amount of resources and scientists such as yourselves available in, say, the Western world,
yep,
to study global climate change, and how much of, or what percentage of that limited resource would you divert to this topic, and what would be the net impact?
That's a good question. So how much should we spend? Ken and I actually tried to say some of this in an article on Issues in Science Technology, which is sort of aimed at an audience of insiders on Capitol Hill. It's a National Academy publication. So you can see, I'll give you a short answer, but you can see a longer answer. But my answer would be, first of all, to start very small. Research programs can be killed by getting too much money because all sorts of nonsense gets funded. And so personally, I would start, no, this has happened before. If you fund, some people are calling for a Manhattan Project kind of thing. That would be a disaster. You'd fund a bunch of craziness, it would collapse. I personally would start at some really small amount of money, like $10 million a year. Remember, the US global climate budget, science budget, is of order $1 billion a year, depending on how you count. So I would start at something like that, so sort of 1% scale at the most. And then I would work my way up, depending on the results, both physical science results and also the way the social science and thinking evolve. towards something of order $50 million a year, which would teach you a huge amount of money and allow you to do some small process experiments if you wanted to and if that was deemed socially significant. So that's the sort of sense of scale. So compared to the total climate science enterprise, I think you could learn a lot with a pretty small amount of money because most of this is climate science. We're basically building on a bunch of architecture that's already been done. It's the same models, it's the same thinking. And I think it is important, and I'm an experimental physicist, and that both means I fall into Burton Richter's liking technology disease, and I admit it freely. But also, I think about the way you can learn a lot about complex systems by manipulation in ways you never can by studying them passively. And I do think, for example, in the boundary layer clouds, that even if you never, ever, ever were going to geoengineer, the idea of putting sea salt aerosols in a modulated way into boundary layer clouds is probably a good idea because you will learn a lot about the key processes that drive those cloud formations that you need for models anyway. And I think that while we don't quite want to talk about it in public, but I'm a guy who likes to say stuff you're not supposed to say, thinking about doing what the ecologists already think about this a lot. Ecologists talk about this kind of designing experiments while you manage. I think we could do some of that for climate and learn a lot. I mean, another example, during the big blackout, the last big blackout of the PJM in eastern US, we took all the power plants offline, but we left the cars. And in the epidemiological studies of what's killing people in terms of health impacts of air pollution, one of the hard things we're trying to do is separate out those two effects. And even from that one experiment, we have a little bit of data, but it doesn't really tell you too much. But if you just put in a little modulation of the amount of power plant dispatch and did it for a few years, not enough to change very much, and at the same time look at the hospital emission records the way we do for all the epidemiology, you might be able to help pull that signal apart. And I think we need to think more about how a little bit of manipulation can teach us stuff about the system in ways that are really useful, that teach us things we need to know about the system we're living in. And I think we can actually learn from the ecologists in that without jumping to manipulating the whole climate at giant scale.
Well, please join me in thanking David for a very thought-provoking talk.
For more, please visit us at stanford.edu.